Thank you. Okay, so what I'd like to talk about today is a distinct feature, maybe the single most distinguishing feature of the sort of models we've been discussing within the arc of this class. So we've been discussing system dynamics models for quite a few sessions now. And we, in the past couple of sessions, have focused on models of contagion. The running sort of exemplar we've used is for contagion of some sort of pathogen, be it bacteria or virus or protozoa or parasite or what have you. But the truth is that's emblematic of a broad class of contagion processes. And not too many sessions ago, I stood before you from around this place in the front, and I mentioned that a defining hallmark of contagion is you having that condition is a risk factor for me getting it. So the fact that one person gets it presents risks for other people with whom commonly they interact directly or indirectly through surfaces or aerosols or what have you, are at risk of developing this condition. But that's emblematic of contagion more generally. And whether it's contagion of conspiracy theories, spread of rumors, spread of malware, spread of radicalizing ideology, spread of ideas, spread of innovation. All these things can be and have been fruitfully characterized as aspects of contagion. And many of the same modeling approaches that we've been dealing with, and indeed those same formulations, end up finding a role in these other spheres. I will note within our bodies as well that people have very fruitfully built a whole subfield around modeling biological dynamics, like dynamics of the immune system and its reaction to invaders, using this same basic mathematical framework. And what perhaps the single most distinguishing feature of all of them is the presence of nonlinearity. We talked about it on this board. In fact, there's probably still bits of chalk that record that discussion. But you'll recall that nonlinearity, you'll recall from that discussion and from the video, that nonlinearity came out in a very specific term, or a very specific sort of component of the SIR model or the SIRS model that we've been dealing with. It came out in a multiplication of what two quantities? Anyone remember? What two state variables? I'll give you a name. Yes, Pius.
I would have said susceptibles and infectives.
Infectives, right?
Yeah.
And informally, I sort of gestured at this by saying, look, if the number of people getting ill per unit time is proportional to, we write it like that, proportional to S times I. If it's the multiplication of this times some constant C's and betas and divided by n, but it really comes down to this is the key thing. The number of new people getting sick per unit time is proportional to this. Then one of the things that it means is if you have no susceptibles, no one's going to get sick, right? If this is zero, it's going to be zero consus. It's going to be zero people getting infected. If there's no infectives, no one's going to get sick. It takes two to tango. You have to have both together. And that's in big contrast to like recovery, where you have some number of infectious people and you have some mean time infectious or whatever. And the formula for this is I over count, where it just depends on this, right? You can analyze just the infectives here and they go up. Here, it's the interaction of susceptibles and infectives that characterizes these nonlinear terms. Now, you may say, well, yeah, also what do you do? Like, so Why is that of significance? Well, it has profound significance in many areas of modeling. In fact, as a motivator for modeling. It's in some ways, it's why we build these models and why since 1916, when Ross first built his models of malaria, in 1927, where Kermit McKendrick first defined the SIR model, people have studied these things to be able to better understand and indeed control, manage, or prevent outbreaks. It's because they exhibit complex behavior. And we've talked about some of those behaviors. And while I'm talking, I'd like you to open up your AnyLogic and download a model that's on the website that is called Endogenous Cycling SIRS Health Service Vicious Cycle Login V2. In other words, look for one that's called, that starts with endogenous cycling on the website, on the campus. But in those earlier discussions, we talked about some distinct features of non-linearity. Can anyone remember one of them? I won't hold it against you, you can, but does anyone remember? Is that a mumble? The presence of, I'm going to use a term here, but I do, like this is good material to be able to testify about in assessment instruments. Tipping points. Situations where the system's behavior will quickly change depending on, now this is a really important point I'm about to make, but don't miss this. Tipping points, we talk about the system's behavior changing as we change parameter value. Okay? Do you remember where we saw this with infectious disease modeling? Anyone? Where it changed like night and day, depending on the value of parameters. Does anyone remember that? It had to do with something called the basic reproductive number, the number of people who contracted infects before they recover in an otherwise susceptible population. And if that was above 1, the behavior would be very different from if it were below 1. What would happen if it were above 1? If I isn't infected, the start of the outbreak can infect, say, 2 people, what's going to happen?
The number of infectives go up.
Number of infectives goes up rapidly. That's right. May go from 2 to 4 to 8 to 16, right? And successively double for a while. Until the depletion of susceptibles limits it, for example, reachable susceptibles. That's a key component. And were you going to say something, Aiden, there?
Yeah, that's very much exactly.
Yeah, exactly. So Nicola merits up with Aiden about that as well. And if the number of people I infect over the course of my illness is less than 1, what's going to happen? It'll, yeah. It'll be right. It'll sort of disappear. That's right. That's exactly right. And in fact, in this model that I've just asked you to open, you will see said behavior. So I'm going to switch to screen sharing here, and we'll go over and enjoy the pleasure of acquaintance, perhaps mixed with this model. So here we have a classic SIRS model of a form that you should well recognize. I've also instrumented it with some observational process, as it were, associated with cumulative infection. So the number of new infections is this, I just used that same value for the number of new cumulative infections, and it just flows into this stuff. Do you see that down at the bottom here? What am I doing there? Mathematically, what am I doing for this cumulative infection? Something, cumulative infections is the under blank of new cumulative infections of the flow. It's the integral. It integrates it up. It accumulates it, right? Right? New cumulative infections is the derivative of this stock, right? If you wrote down the equation for the stock, right? D cumulative infections dt equals what? If I ask you to transcribe just this portion, I give you a pop quiz, just this portion, transcribe it. You'd say cumulative infections dot, right? Or D cumulative infections dt. You could write it either way. Potato, potato. Equals what? It's the flow in minus flow out, right? What's the flow in? New cumulative infection. So the derivative of the stock is this. Stock is the integral of it. It just totals it up, sums it up over time. Okay, that's how that works. Okay, so we have this model. Let's take this model and we are going to run it. I'm actually first going to run it with this. It says baseline 0.75. I stand negligent. That should have been reproductive number 0.75. I don't know why I said it that way. Okay, so I just ran it. And here, the number of, okay, now I'm in trouble. The number of people who have gotten infected, that's actually the bottom one. It says susceptibles, but ignore that label. It's actually, it should be cumulative infectives. It's actually the same number, just almost the same number it started with. It started with 1. Eventually 3 people cumulatively got infected over the entire course of the illness, but basically it petered out. It did not spread in any material way. This is cumulative infection, right? Cumulative infections. So the infection died out here. It's each person spread it to fewer than 1 person on average. And over the entire time, just a couple of people got it and it died out. It didn't catch fire. It didn't go critical. By contrast, let's go look at this top one, the baseline itself. So we're going to go look at this baseline and we're going to analyze over time the number of susceptibles, infectives, and recovereds. So this is the number of susceptibles, this is the number of infectives, this is the number of recovereds, and this is the number of cumulative infectives here, despite the poor label. So you'll notice that early on, the infectives leaped up, and now it's decreasing. It decreased for a long time. But susceptibles are building up, and that allows for a subsequent outbreak. Do you see that? And now the number of infectives is decreasing again. The number of susceptibles is building up, and what do you think we're leading up to? What do you think this is going to lead to? There goes susceptibles, and there's got to be a what? Fuel for the fire is here, and there's going to be an outbreak. And we see another cycle, right? Cumulative infections kind of flattened for a while as there were no new infections, and then as new infections came up suddenly, it built up, and it leapt up, and then it slowly accumulated as infection. People died down. It's flat as susceptibles are building up because there's almost no new infections, and then it's enough to have an outbreak. This shows cycling behavior. So to be clear, we had the parameters such that it didn't take off at all just a few minutes ago. It really only affected 3 people. Essentially, the outbreak didn't happen in any material way. And then you change the parameters to have a larger reproductive number, and we've crossed a tipping point in the infection spreads, but it actually is spreading in a cyclical way. You see this? It's cycling. It's cycling over time. Not because of, the winter is in there or something, but because of other aspects of the dynamics. In this case, because of limited number of healthcare workers and the fact that the more people are infected, the longer it takes them to get treated, and therefore they spread it further, etc. But you see the cyclical behavior. It's qualitatively different than what we had with the lower parameter values. In other words, there's a tipping point in this model. This is one of these characteristics. But I hope to use this model to show you something beyond tipping points. I want to show you lock-in, which we talked about early on in this class. And I want to show you introduce the idea of basins of attraction. Even more foundationally, I'm going to introduce a construct that's going to provide you, dear class members, with a new lens to examine behavior in models and indeed in the world. The lens of state space or phase space characterizations. My focus here will be on applying this in a modeling context, but it turns out we can apply it for empirical data to great and powerful effect, for great insight. I'm not going to go into this in this lecture, but if time affords us, if the time allows at the end of the class, at the end of the semester, we will talk about that. Okay, so we've seen two modes of behavior here, governed by parameter values. I want to show you a third mode of behavior. Okay, and this one is going to be governed by not just parameter values, but the actual state of the system. Can put the model into this state. Maybe to reflect on what we've just seen. If I have a basic, if I set the parameter such the basic reproductive number is 0.75, the way I did that is I set contacts to be half their baseline value. And I set the chance of transmission per contact to be half of its baseline value. And that made the reproductive number of less than 1. Okay. That meant the infection didn't spread. Okay. Let me ask this. If I had started the model, if I had started that model with lots of people infected, maybe instead of 1 person initially infected, I started with 100 initially infected, or indeed 1,000. What would have happened then? Well, in general, for SIR type models, if 1 person can't spread their infection efficiently, then he can't infect more than 1 person. 1,000 people is also not. Yeah. In fact, there's going to be even fewer susceptibles for them to infect, because those who are not infected, we might posit start susceptible. And so the truth is, it will die out. Regardless, it's a matter of the parameters. It's a matter of factors such as these here, these contacts per day, probability of transmission per discordant contact, time until they present for treatment. If those are too low, doesn't matter if you start with 10, 100, 1,000. It's they're not going to spread their infection effectively, and the number of infectives is going to peter out just at the beginning, just as it did with 1. So there might be a few infected along the way, but it won't be too many in general for an infection, in an SIR type model. But what I'm going to show you is a situation where we can have the system exhibit different behavior based on the values of the state variables, where if we have the right combination of values of the state variables, it can exhibit very different behavior. And to understand this, we're going to use the concept of a basin of attraction. And to introduce that, I really need to tell you about state space and the state space lens. Okay. So what we're going to do here is introduce a little bit of a picture of state space. Okay. So pardon me, I've just lost my place in this document, and here we go. I posted these slides if anyone wants to find them on Canvas. Okay, so when we looked at model behavior just now, we interpreted it in light of graphs over time, right? So we have something like time as the x-axis, right? And then we had various curves, maybe number susceptible, maybe I'll use a green for that. Number infective, maybe reddish for that. And the number recovered, maybe yellowish for that, something like that, right? Over time. We comfortable with that? Now, each of these I'm going to call a state variable, okay? State variable. I mean, this one happens to be recovered. If we could say that it's the value of a stock, and that would be true too. The generic term for it is state variable. It's an aspect of its current situation, its current state. We comfortable with that? So this is the most common lens people use to understand behavior of the model. I say lens because it's a way of kind of looking at model dynamics and understanding it and visualizing it. But it's not the only one. And there's a powerful lens of another sort that's called the state space lens. So state space allows us to depict the behavior of the model over time in a way that's very powerful. So here, instead of having time running one way and the value of a variable, we're going to have a coordinate system that might be, for a given model, the number of, maybe we'll do susceptibles here, infectives here, and then going into the board. Imagine kind of an axis going into the board. Sort of running, as it were, running that way. We'll put R. And at any one point, the system will have a certain value of susceptible. Number of people susceptible at any one time, right? At any one time, the model will have a certain number of people susceptible. You follow that? Certain number of people infected, and at this point will be further into the board or further out of the board, depending on the number of people recovered. So I'm saying at each point in time, the system will be at a point. You got that? And the system's behavior over time, the system's evolution will move. For example, if more people are becoming infective, the number of infectives will be going up. So this point will be going up. But as the number of infectives goes up, what tends to go down? That's also found here. The susceptible. So it might be going up here at a 45-degree angle, right? We go up because we're gaining infections. More people are currently infected, and we're losing in terms of there are fewer and fewer people susceptible. So it's going up at this angle. And the rate at which it's going up, so the angle of this is set so that this vector is proportional to I dot, S dot, and R dot. In other words, this will be going up at a very fast up here, big vector up, it might be shown as if I dot is really large, it's gaining really quickly. The other hand, if I dot is very small and S dot is correspondingly not changing that much, we might have a very small vector. So commonly we set the angle, we either make the vector sort of longer when we plot it out, if these values are larger or smaller, at least we keep the angle between them, because the angle between them will indicate how much this is changing relative to this is changing relative to this is changing. The rate of change of S of I and R. So this is the basic idea of state space. I'm going to show you some examples. Are we comfortable with this idea? Yes, Pius.
So is R like the equilibrium of where this thing should be?
No, what's going to happen is great question. There will be an equilibrium. So the system will typically evolve. Let's suppose it started, well, I'm going to ask you, suppose it started with everyone susceptible and only one infective, and no one recovered. Where would that start in this diagram?
Right.
Yeah, it'll be way out here to the right, susceptible. It'll have almost no one infected, so I will be very close to this axis, right? And R will be 0, so it'll be right on the board here. It won't be in. Over time, people get infected, so I will be going up, S will be going down, almost in a 1-to-1 basis. So it'll come up like this, right? Come up with this sort of angle. What's going to happen then is going to depend on the model dynamics, like form, and we'll see several examples. For example, it may go here to a new equilibrium where there's nobody susceptible, nobody infected, but everyone recovered. Or it may go up for another system to a situation where it will spiral into an equilibrium where it's in balance, where there's a certain number of susceptibles, a certain number of infectives, and a certain number of recovered. I'm just introducing the idea of state space here. The point is, it's an alternative way of depicting model evolution. Each of the axes, so the state space depicts some n-dimensional space, where n is the number of stalks here, number of state variables. In a given run of the model, I said, a given simulation, a given numerical integration of the model is a trajectory in state space defined by this sort of curve in state space, right? I said it before, it's following the curve. And what curve is it following? Well, that dictated by the derivatives, S dot, I dot, R dot. Time is not explicitly shown. You notice here, time is actually one of the axes. Is time one of the axes there? No. But at any one point, it will have a certain time. So like here, it'll be at a certain time. Here, it'll be at a certain time. It's not shown. And it may dwell for a while in a certain area, you know, maybe going very slow here or something. And so there's lots and lots of these points here, but here it's going quite quickly, right? So time is kind of implicit. Okay. And time is moving on, so I'm going to show you. So this is an example of a state space depiction. Now, one of the things that you start to get out of it, and that recommends these, one of the many virtues that recommends these diagrams, is the fact that you can depict at each point in state space where the system will go if it's at that point. Right? You could say, well, look, if there were 100 susceptibles and 30 infectives, let's suppose this was an SI system, or let's suppose it was an SIRS system with a fixed size population. So if you know S and I, you know R, n minus F minus 1, then you could figure out what S dot is. You can figure out what I dot is, like the rate of change. right? And you could say, okay, you know, I dot is bigger than 0, so it's going up. And S dot is less than 0, so it's going to the left, look fewer S. So you can draw in this little arrow that will show where it will go next, And you can do this in the entire diagram. Highest S, presciently. Where, you know, how equilibrium will appear. This is one common place in equilibrium. How an equilibrium will appear. It's cycling around this equilibrium. That behavior over here on a time plot could appear as a cycle as it approaches some equilibrium in terms of S, in terms of I. Here it will appear as sort of a cycle around a point where it's getting closer and closer to a point where it's in balance. When it's actually at the equilibrium, the system is in balance. There's no change in S, there's no change in I, there's no change in R, so it'll just stay here. It'll just stick here. Yes, Gina.
Say like backwards.
Yeah.
If this is,
Yeah.
if the state space diagrams for a specific run.
Yeah.
That only applies.
Correct. Yeah, the blue here shows a specific run. I'm saying that in the tools we have more generally, beyond just running the model one at a time, you could actually calculate this, or by running the model, if you really wanted to, by setting it up, you could set the model up as its initial condition to be here. You could set it up as its initial condition to be here. You could set it up and see what does it do next. But with the equations, like you've been learning to transcribe here, you want this to be a skill everyone has, you could actually calculate. You could plug in numbers for M. You could plug in numbers for I. You could say S equals, 57 people. I equals 19 people. R equals the rest of the people. And you could calculate, if you know the values for delta and beta, or C, or etc., you could actually calculate what I dot is, what S dot is from this differential equation. And those would tell you what direction the arrow to tell you where it goes next, So when you have a system that's described symbolically, like you're learning to describe, in this very pop quiz, you're learning to write down the equations that allow you to say how, for any combination of S, I, and R, where the system will go next, what its next step will be, what its next, evolution will be. And you can, from that, actually, plot out a diagram like this that maps out globally how the system can behave. Now, I'm going to ask you a question. With those equations that you can write down, and as you're increasingly good at writing down, you can literally plug in values for S, I, and R. And as long as you have values for delta, alpha, whatever it is that I give you for parameters, you could calculate S dot, you can calculate I dot, you can calculate R. You can calculate how it will behave. Can you do that for an agent-based model? Not in today's ways of phrasing agent-based models. You can't. You could set it up in a certain state. You could let there be, right? Let there be this many systems. You could put them in that state, put them in so many in the infectious state or whatever. Established networks, and we could measure, but it would be harder. It's not quite as easy mathematically, not as transparent mathematically. It can't just be calculated directly, sort of what the value would be. But here you can. Now, time runneth on, and we need to we need to steward our time well. But what this allows us is a very powerful means of seeing almost in stereo. We can view things through a time-based lens, and this is incredibly valuable insight. But we can view things alongside that with a lens of state space. And that too is very insightful. That too is powerful. And they actually are powerful they have different balance of benefits that they bring. But I want you to be able to learn what this means. So when you see this, it shouldn't just be a buzzing, blooming confusion of arrows, every which way. This describes the logic of the model. This describes the dynamics of the model for different combinations of state variables, where the model will go next. And the direction of this arrow and sort of how fast you go along it is dictated by dx, dt, dy. Right? If dy dt is, and you'll be going up quickly, right? If dy dt and dx dt are very small, it'll be going, to left in a very slow sort of way. And the angle is set as based on the relative size of it. You notice over some areas of state space here, it's going up and to the left. Some areas it's being pulled down to the two. So we can see the dynamics of a model in through these two different lenses. Okay, now, as I noted, equilibria can appear here, and equilibria lead to, with equilibria with a time-based plot, what does an equilibrium look like? It looks like, if you said it informally, what would it look like?
A state that appears not continuous.
Yeah, a flat line, right? Just flat line. Keep on going. Here, what would equilibrium look like? I emphasized it before, but I want to make sure it's sunk in. It would be a point, and it wouldn't change. It would be what we call a fixed point, an invariant point. A point, fixed point is a good word for it. I love seeing people taking notes. So it's a fixed point. It's a point where if you put it there, the system doesn't change in its value going forward. Now, I'm leading up to a reveal about nonlinear systems. All these systems I'm looking at here are actually linear. And if I might say so myself, I still think linear behavior can look pretty cool on state-space lenses, right? With these sort of cycles, but this is actually linear behavior. This behavior is nothing to this behavior still allows us to take the system apart into pieces and describe it separately for different types of people in the system or what have you. There's not this sort of interaction we see with that term S times I in a nonlinear model, for example, for communicable disease. The behavior of the system in terms of the hazard rates is independent for linear systems of the state of the system. We have linear dependence. We have things like first order delays where the number of people leaving a state is proportional to the number of people in the state, right? This is linear, right? It's a constant times this state variable. We say it's linear, proportional to the state variable. Okay, now when we enter the nonlinear realm, we actually have much richer behavior in general. And if I had my druthers, I would launch in right now to a more fulsome treatment of this topic. And it would provide me joy and happiness that might not be universally shared across this class, but can actually lend a lot of insights. And this concerns the fact that when we have nonlinear systems, the system's behavior will change over and across the state space in quite significant ways. It will look linearly around certain areas of the state space commonly, but that behavior may differ quite a lot. Okay. And I give some examples there. So for an SIRS model, type of model with which you are increasingly familiar and hopefully is your friend and not your enemy, we can have behavior that includes the following. So here we have susceptibles and infectives, and as susceptibles, as people get infected, there are fewer susceptibles, more infective, so it sort of travels up. But then you get recovery going on, right? And so there can be fewer and fewer susceptibles, so it's fewer and fewer infectives as well, because more and more people have recovered, and then it may go to a equilibrium here. What I'm not showing you, though, is where it gets really interesting and where we have different basins of attraction. Okay. And I'm going to need to describe this using a bit of a depiction on the blackboard. With apologies to those in that far side of the room. So if we depict a state space, you'll recall that state spaces, the axes for a state space, the dimensions for a state space, if I could use that word, which is awfully overloaded, can be given by the values of the state variables. That's what makes it a state space, right? I will note, for those from physics background, or anyone who's taken a number of math courses, it's possible you would have heard the term phase space there. And it's largely, it's basically potato. It's essentially the same idea. So here, I'm not going to try to draw our R going into the board, but basically we have a space delineated whose coordinates are given by the values of the state variable. And what I'm telling you with the idea of basins of attraction is there can be different regions of the space for a nonlinear model specifically, which are governed by different behavior. So if you're in this area of the system, maybe it goes to an equilibrium that has fewer infectives, more susceptibles, and a certain number of recoveries. If you're up in this area of the space, maybe you'll go to an equilibrium that has many more infectives, or it has almost comparable number of susceptibles, but fewer recoveries. That's really what's not being shown here. And the idea is, depending on which side of the line you're on, depending on your state, not merely your parameter values, which made the tipping point. And remember, if we had C and beta too small, it would die out. If we had C and beta large, it would take off as an outbreak. Do you remember that idea, as I introduced earlier? Very basic, this idea of a basic reproductive number dictates whether it takes off. Here, depending where you are in the state of the system, you can have very different behavior listed. Sometimes you might have, 3 different areas of state space, where this one has higher infections yet, and if you are in this area of space, you're attracted to this attractor. If you're in this area of the space, you're attracted to this attractor. If you're in this area of the space, you're attracted to this attractor. It's like, that's what we call basins of attraction. These are areas of the state space that the system tends to evolve in. But they're in a nonlinear system, there can be different ones that it evolves to at different times. Now, I'm going to show you for this particular model in our closing minutes. All four of them. We can have this. This is actually a picture of sort of an equilibrium here up close. What I'm going to look at, though, is our particular model. And we're gonna do an experiment. So we saw, do you remember we saw that behavior for the baseline where it cycles? Do you remember that? We set the parameters to be to have much lower contact, much lower risk of infection per contact, and it died out, or we could set it to its default values and it cycles, right? Do you remember this? And it was cycling, and initially the number of infectives initially took off, and then it died down because the number of susceptibles was very, very low. Infectives recovered, more recovereds go up, and the infectives come down here. And then at some point, there's very, very few infectives, susceptibles build up, and it sets the stage. Okay, somehow here we are. Okay, so what I'm going to do, I think we remember this behavior rather well from a few minutes ago, right? You notice the susceptibles are building up, and it sets the stage for a new outbreak. Okay, remember this? What I'm going to do is I'm going to set the number of infectives within this model to a far larger value, okay? I'm going to set it, imagine that we have Deus Ex Machina, a very, very large fraction of the population that becomes infective. So I'm going to say 150,000 of the population are infective. And I'm going to reduce correspondingly the number who are recovered to about 49,000. Okay. So I'm setting it into a state with very large number of infectives, very large, many recovereds, and then very few infectives. Now, this state, oh, okay. Oh gosh, I wasn't able to, there we go. So there we go with dynamics. It's actually able to bounce back. I actually was not fully anticipating it. If I reduce here, and this could be gained if I set the model state to a low value, but if I reduce the number of healthcare workers here to a very, very low value, then we can get it in a very different state of the system where we have very large number of infectives, very few susceptibles, and a comparatively large number of recovereds. It's actually gone into a very different equilibrium state. It's no longer cycling. It's just being constant. And we've gone from one which has a limit cycle down here around it, where it's just cycling around in some periodic way, a point here, to a situation where it's gone to a static equilibrium of very, very high numbers of people infected, right? We have here the number infected being up nearly 100,000 here, about 95,000. So what I'm saying is there are different basins of attraction. This is a system which still exhibits tipping points in terms of if the base reproductive number is too low, it won't take off in terms of parameters. But it can also be placed into different areas of its state space where it finds different equilibria. Here, it goes to this limit cycle and cycles around it in this very periodic fixed way with susceptibles building up, an outbreak happens, the outbreak lowers the number of susceptibles, the effectives go down for a while, and then susceptibles build up and it repeats. That's this one with a so-called limit cycle around it. It actually does not reach a fixed equilibrium. We sometimes call this a dynamic equilibrium because it's in a sort of final state, but it's cycling. It's not a single final state. It's like an orbit around us. This, by contrast, that it's in now is a fixed state. It gets to the point and it just stays there in a fixed way. Those are two very different basins of attraction this system can be in. And that's a result of non-linearity. That's a result of the system having these multiple basins of attraction where different dynamics govern it. And that's only possible for nonlinear systems where the governing dynamics are described by different linearizations for different equilibria. They evolve in different ways. Okay, that's all we have time for today. Thank you for your patience. I'll discuss the answers to the pop quiz next time, and we'll continue on our learning journey with another nonlinear model involving predator-prey. Thank you. Yes, Nicola.
I just want to make sure I understand, like, for non-linear and linear systems.
Yeah.
If it's a linear system, the
Yeah.
variable